All right, hello and welcome to Data Science CastNet. In today's video, I'm very excited because we have a guest here. Grace is the first author on a couple of papers that I'm very excited about, and so we're going to be diving into that. Grace, would you like to introduce yourself briefly?
Yeah, thanks for having me, Jonathan. So I'm Grace. I am a computer vision PhD student at UC Berkeley. And recently I've been really interested in analyzing the internal representations of generative models and seeing if we can use them for things beyond just image generation. So if you can tackle a lot of, canonical pre-existing computer vision tasks with these really amazing and powerful, like large models.
Cool, excellent. Well, do you want to show us your entry into that space then?
Yeah, so I guess I'll share my window. Maybe
From
I'll do even a more historical view. So I like kind of prepared two papers in terms of our diffusion hyperfeatures paper and readout guidance paper um, for different ways in which we like probe the internals of diffusion models. But actually, there's this paper that maybe is a bit lesser known that I also did kind of in my first year of the PhD, which I think was like the jumpstart into this whole like internal representations of generative models kind of idea. So I'll just start there.
cool.
So basically, this paper is called Shape-Guided Diffusion with Inside-Outside Attention. And it was heavily inspired by kind of a work before that came out like very recently before called Prompt to Prompt, which basically shows if you take the like cross-attention map of like a reference generation and you copy it over to a like new generation that you can like imitate a lot of the structure and kind of have this like structural similarity between the two. And this makes a lot of sense. I don't know if I should maybe present the paper so that it's like easier to visualize what's going on. But prompt to prompt was like particularly exciting because you can do these applications of essentially, I have a, let's see, I think they had some kind of more interesting ones. Uh, So basically you have like an input image, for example, of these apples, and you can generate a new image with a new prompt, but preserve a lot of different structure elements. And the kind of key intuition is just that cross-attention maps heavily influence structure. So for example, there's this bear, and you can see that the cross-attention will heavily like attend over the bear.
Okay, and so just to like dig into what we're visualizing here,
Hmm.
across the representation of the image and at different resolutions, it still like has this X and Y idea. Certain parts of that are being influenced more strongly by certain parts of the prompt, right? And so we can get this localization and say, oh, these red parts of the image here, these are the parts of the image that are paying attention to that bear token, right? They're heavily like influenced by that. And so that's a region that if we were going to edit out, if you said change the bear to a lion, we could use this spatial layout of these internal features, like which ones are activating for this input. We could use that to steer the process somehow and to guide what's going to be edited, what's going to be replaced, that kind of thing.
Yeah, that's right. It's essentially this like association between, like you said, these like spatial regions and a particular token. And so if you wanted, for example, to make a line in a really similar structure, you would probably want a very similar region of the image to be affected by the token lion. So that's exactly the kind of intuition. And so that's also a key intuition that we use in our shape-guided diffusion paper, where now the task instead is to do this kind of more like in painting centric task of, let's say we have this real image and we only want to like edit the image within some input mask region, then our method is able to do this a bit more faithfully. And again, it's based on this whole association idea. So maybe to dive briefly into the kind of like mechanics, essentially what we do is we take these same attention maps and essentially we kind of enforce that a token, for example, dog, would only attend or like have this attention map over this internal mask region, and other dog or other tokens such as like background would attend over like the non-mask region. And so to kind of enforce this locality of like dog should only affect, the dog region of this like real image, and like background should only affect the background region of the real image. And so by having this like stronger localization of like a given token for only attending over this like region as specified by user, this mask region, then we can do like more faithful, shape preserving edits. Um, and so I think that's the most kind of interesting tidbit from this paper in terms of these internal representations are very powerful, and if you can like manipulate them in one way, then you can do a lot of really interesting applications. And so after that paper, then it kind of shifted gears more towards, okay, so we did this really cool paper where we looked at the internal representations and then we used it for a editing task, which is still very close to image generation. And so now the question is, okay, can these features be useful for things beyond just image editing, just like a canonical discriminative task that people have, tried for a very long time, but instead with this generative model and its features. And so that kind of led us to diffusion hyperfeatures, where we essentially used the internal features of the diffusion model. We aggregated them across the different layers of the UNet, as you presented, as well as over the time steps of the diffusion process. And we essentially trained this kind of like aggregation network on top of this frozen set of features to interpret it into a task-specific representation. So in this case, it's for the task of semantic correspondence, where essentially what you have is a input image on the left and a target image on the right. And so for a couple of key points on this input image, we want to correctly locate the key points in this like target image. So for example, if I have a foot on one dog, then I want to correspond it to the foot on the other dog. If I have the tail, I want to correspond to the tail. If I have, the eye, I want to correspond it to the eye. So this requires this kind of very general knowledge of objects and kind of semantically what subparts they have.
Yeah.
In order to do this, correspondence task.
If you showed this to a computer vision researcher in 2010, their minds would literally explode, right? Because there's nothing about those two images that's the same other than that they're dogs. And so the back left foot of the dog, like on a pixel level, has absolutely nothing to do with the back left pixel of the other dog, right? Like the different colors, the different shapes, the different textures, everything. It's a different orientation. And yet somehow the model is able to, like, hopefully, like the task is, can we like tag both of those points as being similar somehow? And so when you say semantically, you mean like, oh, it's not similar, they're the same color, it's similar, they're the same thing, like they have the same kind of intrinsic meaning. It's actually an incredibly hard task, this kind of correspondence.
Yeah, it's a really hard task. And one really fascinating thing is that for the longest time for correspondence, people were using this thing called SIFT, which is exactly like you said, this kind of very pixel level statistics of this like pixel region is very, similar in terms of statistics to this like other pixel region. And people still often use this, especially in 3D, where essentially you do have very similar pixel statistics between two images because you're usually considering like multiple views of the same scene. But I think when you get to this case of two like very different scenes that look so different like this, then you definitely need like a very rich feature space instead of looking at these pixel statistics. Yeah. So I think I'm trying to think of what other interesting things are to like go over in this paper. I think the maybe most interesting thing is essentially, with a little bit of fine tuning on this task of semantic correspondence, we're able to achieve state of the art against other kind of like supervised methods that only train on semantic correspondence on this task, which is super interesting. And so these feature maps are also very dense, so you can use them for kind of like warping. So this is essentially saying for like the feature map of the source image and the target image, if you do this like nearest neighbors matching of like for every point on the source image, what is the nearest in the target, and then you kind of warp it, then it can do pretty nice warps, which is fun. So that's neat. And yeah, I think that's an interesting paper showing like the power of the features of these like diffusion models.
So maybe one thing that's worth pulling out, there's been previous papers before diffusion hyperfeatures that did something like, okay, so let's say we want to do segmentation. So I want a pixel-wise mask label or something like that. So what they would do is they would start from a pre-trained diffusion model that generates images, and they would fine-tune it on this new task, which is to generate like segmentation masks or something like that. But there you're rewriting the whole network. So you're hopefully like keeping some use of the existing features that it's learned, but it's not having to learn this completely new like output task. And so it's a very like heavyweight change and adaptation to the network. And I think one thing that's quite different with your approach is, you said it's very lightweight and it's kind of on top of this frozen backbone. Maybe I think in the paper you did some like PCA on the features and showed that even without like any training, just literally like taking the most, the top few principal components.
Yeah.
Yeah.
Yeah. Yeah, so that's a good point. So I think we have some PCA visualizations, for example, figure
Yeah,
two,
there we
where this
go.
is essentially like you're saying, like the raw features are able to already do this correspondence task. I also want to shout out actually like a prior work that heavily influenced us to even like do this paper or like investigate it in the first place, which is called Plug and Play, where they essentially did a lot of these really similar PCA visualizations, and kind of demonstrated that these like raw feature maps from the frozen model are able to relate these
Mm.
like objects of a similar semantic category in a very robust way. Of like if you have different humanoid objects, even things that are like Elmo that don't really look that human, then you can still do this kind of correspondence. And so, yeah, it's like very fascinating how essentially even these raw features are like pretty great at this task. So we also have as a baseline in our paper actually just the raw features themselves, which already perform, on par with some very early supervised semantic correspondence methods, for example, DHPF. If you were to compare it to the raw features from only layer 4 or like some concatenation of them. And so that's pretty fascinating. I think, like you said, there are some other methods that might have to do, full fine tuning of the network because this information might not be as readily available in the raw features.
Mm.
I think it really depends on the task and like how readily available this information is.
Yeah.
So essentially, something more like semantics is something that is better encoded in these raw features, likely because, to generate different images of cats, it like kind of draws upon this common understanding subparts a cat has and so forth. Yeah.
Very cool. And then maybe like one last thing before we move on from this paper is that we should also like, so we're talking about these features. If I'm like going old school and I'm saying, oh, I'm using some CNN to extract features, which I'm then going to use for similarity search or something like that. The picture is like the image goes through the whole network, and then I just slice off the final like classification bit, and I get one vector. It's 512 numbers or something like that.
Yeah.
But in this case, it's definitely not like that, right? So we have these multiple layers that at different resolutions. So their outputs are 8 by 8 or 16 by 16 or 64 by 64. And then
Yeah.
also you mentioned that it's across time as well. So maybe
Yeah.
just paint me a picture, like what is the shape of the set of features that's coming out of the model, and then after your aggregation, what is the shape of that?
Yeah, so that's a good question. I think maybe even before we go into like the little tidbits. So I think this point about, prior classification methods and where you extract the features from, this is definitely like kind of a like manual process that people kind of figured where they were like, oh, if I just take the last like set of features, then it performs very well in my like classification task that I care about. And so I think the thing about that is that it's like manual, it's not necessarily automated. And so the kind of design of our method in this diffusion hyperfeatures paper is kind of saying like, where the best features are might be a function of both your task. So is it like classification? Is it correspondence? Is it something very like higher order, like textures, or low order, like semantics? Also, what's your base model? So if your base model is kind of like a UNet, then in general, the more semantic information is going to be in like the center at the lowest resolutions, versus like other methods such as like transformers or vision transformers, the location of where the best features are might be very different. And so that was kind of the motivation for why we used an automatic procedure for selecting the best feature maps, and therefore considered like as many feature maps like as we could in the network. And so in terms of the actual like shape for this like particular diffusion model UNet architecture that we were investigating, so basically this is stable diffusion. And so the way it works is that you have like a series of encoder layers, a mid layer, and then decoder layers. And so for the purposes of our investigation, we only looked at the decoder layers because prior works kind of said that those were where the best features were. And so each kind of progressive layer of the decoder is a different resolution. So I believe like the mid layer is something like 8 by 8. then it's 16 by 16, 32 by 32, 64 by 64. So it's kind of like progressively different resolutions. And not only that, but they also have different channel counts in terms of their feature maps. And so in order to kind of like handle the fact that we have this very like heterogeneous set of features, what we do is we essentially to handle the like resolution issue where everything's a different resolution, what we do is we simply like bilinearly interpolate these feature maps to be some like fixed spatial resolution, which we find performs reasonably well. And then in order to handle this, difference in channel count issue, we do have like in our aggregation network, this set of layers or convolutions that convert from the original channel count from the base model to some like fixed predetermined channel count that we choose. And so our aggregation network, therefore, is very lightweight in parameter count in the sense of our layers are mainly dedicated towards like standardizing this channel count. And once we have these standardized feature maps, what we do is we simply average them across all the layers and time steps to produce like a singular feature map. And the last thing we learn is essentially these things we call mixing weights, which is like how important is a particular layer or time step for this task to kind of upweight the ones that are more useful and downweight the ones that are less useful. Yeah.
Cool. Thank you.
Yeah, okay, cool. So finally, I can go into our readout guidance paper, which is like a culmination of a lot of these ideas of, the first paper that's trying to do this editing task, the second paper that's trying to do this more discriminative task. And so with readout guidance, we kind of found that diffusion models are really great at these discriminative tasks. They have really great features. And so how could you possibly use them in order to, control your generation or make your generation better? And so the idea is, okay, so if my diffusion model can literally tell me the pose of a person, can I just use that fact to be like, okay, then make the pose of the person like this, like according to some input. And so that was the kind of thing that we developed in this paper and showed how you could go about doing that. And so essentially what we did is basically took a lot of kind of ideas from diffusion hyperfeatures and adapted it so that it would be more appropriate for this control-based task. So to summarize like how we go about, for example, doing pose control is we'll take this base diffusion model, we'll take these frozen diffusion features from across the network, and then we'll again train like our little aggregation network, which we now call like a readout head, in order to predict some property. So in the previous paper, we were trying to predict like this property of semantic correspondence. In this paper, like a new property we might want to predict is simply like pose of a person. And so what we do is we train it on Pascal VOC, and we train it on these kind of like pseudo labels from a pose prediction model called OpenPose, because, for example, Pascal VOC doesn't have ground truth pose annotations. And so this is like an example of how we do this like pose estimation task. And so once you're able to get what we call like a pose readout, or like for this given image, kind of like understand what the pose of it is, then you can do the guidance part, which is essentially saying like, okay, so let's say I have this like new pose that as a user, I really want my image to kind of respect. So this is an example of we have an image, we ran OpenPose on it, and we got the actual like raw OpenPose prediction. And our model is able to understand this kind of like pose output space, where we apply a loss during the diffusion sampling process to encourage the kind of estimated pose of the image that we're generating to be very similar to the input that we had as a user. And so that is, kind of the manifestation of how you can use these like discriminative abilities in order to do better, more controlled generation. And so we also have like different applications beyond, very canonical spatially aligned control as, popularized by ControlNet. We also try other applications such as drag-based manipulation, where essentially in order to do a task like this, then you want one head for this like correspondence task. So very similar to diffusion hyperfeatures, except now we train it on videos from Davis, whereas our previous paper was training on, these very different images from this data set called S-pair. And the other thing that we do is you also need like an appearance similarity head to have this like appearance preservation, which we also train with this triplet-based loss on the Davis data set. And so by simply using these two kind of readout heads, like so one for correspondence, one for appearance, then we're able to do these drags of like essentially, okay, I have this nose, I want to move it up for this like synthetic image. And you can also do it for real images. So essentially, if you have like this image here, this was kind of fun where I like ran a point tracking algorithm. And so these are like example point tracks from, this was like from a real video.
Mm-hmm.
And so you can like, again, handle, multiple input correspondences and like make it respect this kind of motion, which is really fun. Definitely requires a little bit more engineering to operate on real images. So you have to do like fancy stuff called like DDIM inversion. And that sort of thing in order to get it to work on the setting.
Cool. Okay, so there's lots of moving pieces here that I want to go back to and dig into a little bit more. And
Yeah.
maybe it's fun to like contrast some of these pieces to previous work. So for example, you
Hmm.
just very casually here create a way to predict the pose given the image. And
Hmm.
the way that you would historically do that is you would try and gather millions of images with annotated poses, right? You'd pay armies of labelers to
Hmm.
carefully hand animate a bunch of images. Then you'd start from scratch and you train a network that maybe produces, a fixed number of outputs, and then you do
Hmm.
compare those to the human labels and update. And instead, what you do is you say, well, we already have decent pose estimators, so I'm just going to use that to create the labels. And I'm just
Hmm.
going to do it for a few hundred images. And
Hmm.
all I'm going to train is this aggregation network, basically, that takes the
Hmm.
existing features, it's remapping them, and then it's uh, changing the number of channels and like projecting them down. But
Hmm.
but it's a very simple network on a very few examples, and those examples in this case, you're like, oh, I can already synthetically generate them.
Hmm. Yeah.
Yeah, so it's a very different approach to like the traditional way. It's like, oh, I'm leveraging this pre-trained beast. I just
Hmm.
fit my little thing. I get a few examples, and then bam, you have an amazing like pose estimator, right?
Yeah. Yeah, that's a really great point in that this is, very data efficient in a sense. Like you said, you don't necessarily need that many examples to get good poses. I think we have some examples in the paper where we essentially ablate, if you train on 100 examples versus 1,000 examples versus 10,000 examples, how do your readouts change? So I think it's cool to maybe look at both the readouts and the generations. I think yeah, we have this like very large table of examples at the end of the paper where it shows like the quality of
Mm.
how you're able to like respect the guidance if you train on like 100 versus 1,000 versus 8.5 thousand. Um, and then we also have that, I guess, in the main paper as well. But still, if you train on more data, it does work better. So we
Yeah.
have that in this kind of like figure where it shows like, okay, if you like were to train it on more data, it like kind of linearly improves the
Mm.
PCK or the percentage of correct key points in terms of being faithful to your input pose when you're generating the image. So it's kind of like the faithfulness of the generation.
Mm.
Um, but yeah, so maybe to dive a bit more into, for example, like the architecture of the pose head and why it's particularly interesting. I think the first thing is that we made it pretty simple in order to handle a bunch of, different kinds of tasks beyond pose estimation.
Mm-hmm.
So we made it very task agnostic in that, for example, one thing is that this output kind of object is not actually a traditional joint representation that you would normally use for pose estimation. It's actually an RGB image. So what you see is literally the output
Yeah.
of this model. And so the reason why is because, if you represent it as an RGB image, you can use the exact same architecture for like depth or for edges and so forth. And the only thing that you're changing is just your like target or your objective.
Right.
Um,
And we've
and
seen
so
other
that,
works that do the same thing for normal maps and for edges and for, like, yeah, all of the anything where, oh, I have an image and I want to create, the lighting and the albedo and all of these like
mhm,
intrinsic scene properties. Um,
yeah.
it's like it's almost like the networks had to learn all of these things about how the world works, how things are spatially arranged, what people look like, just to be able to generate them. And so yeah, you're able to like, oh, okay, if we take these features and map them to an image-sized thing, yeah, if we annotate that with what we want and that happens to be poses, it's very happy to take what it knows about poses and map that to that output. It's staggering that that works, right? It's quite incredible that this generative task, it's learned all of these things that we can now remap for all of these other kinds of readout purposes.
Yeah, definitely. I think exactly like you said, it seems like, being able to do these subtasks, such as like knowing the pose, the depth, or the edges, is kind of like a stepping stone in order to produce the good images. I don't think it's definitively clear, like in order to produce good images, that you like always do it this like right way, which is like grounded in real world like 3D properties of like how things are. But it's definitely kind of demonstrated by the strong abilities in like predicting these image properties like from images.
Hmm.
I think also one kind of side note, I don't know if it's interesting, but I have been trying to train, a more canonical type of like pose head where you actually do try to predict the joints as opposed to these like RGB images, just to benchmark the ability of our method on the actual like pose prediction task. And it seems to perform pretty like reasonably. So I don't think it's like necessarily like, oh, you should always like predict as RGB images versus like the original task specific representation. I think just in terms of like generality and being able to do lots of things, the RGB is like way easier to use. That's also actually how control net, like
Hmm.
encodes these like input conditionings, is that it only does it in RGB images. So it can like handle a lot of different types of tasks. But yeah.
Cool. Yeah, no, I know. So I'd done some. So this is how we met and how we ended up talking about this. Is that I'd also done some
Hmm.
some reading out where the readout was an aesthetic score,
Yeah.
and then using that for
Yeah.
guidance. So you can definitely have like, oh, I just want a single number or like a class. I know someone else who did like head pose, but it was like vertical angle and
Yeah.
horizontal angle as two individual
Yeah.
numbers. But yeah, it's very
Yeah.
cool, and I think the like treat everything as an image. That's very like very deep learning researcher. Like, oh, just make it all the same. It's so much easier. Audio, it's a spectrogram. It's an image. Pose, yeah, it's RGB. It's an image. I love it. Excellent. Okay,
Yeah. Yeah.
so this is the like the readout part, and that already in itself
Hmm.
is super fascinating, and I think there's lots of other papers like focused on that. You do
Hmm.
magic trick number two in the same paper, which is like, oh, now that we can sort of like predict these poses, you then say, can we use this to steer the generation?
Hmm.
And so maybe now we can go back to the
Yeah.
guidance pass that you kind of, yeah, you illustrated
Hmm.
there. And so I'll try to explain this to you, and then you can tell me, yeah, that makes sense.
Hmm.
So while the network is generating, it's starting from like random noise. Um,
Hmm.
it's processing that noise to make its predictions for what the final image should look like.
Hmm.
And in processing that, it's also producing features, right? You can say, oh, by the way, while you're making that prediction, just store
Hmm.
the outputs of these different layers.
Yeah.
Then you've
Hmm.
already trained a thing that says, well, if I know the outputs of those layers, I can predict what the pose looks like, right?
Hmm.
So you
Yeah.
have that building
Hmm.
block in place. And then you say, okay, at the moment the pose is looking like one person going like this. And what I actually want is a
Hmm.
person going like that. And so
Hmm.
I'll measure the difference between what I want and what I currently am predicting.
Hmm.
And then
Yeah.
I'm gonna everything is differentiable. I'm keeping track of all the gradients.
Hmm.
I'm gonna tweak the starting latents um,
Hmm.
based on the gradients to say, I kind of like the pose to look more like this. So I'm going to trace that error
Hmm.
back. I'm going to update those latents, and then I'm going to
Hmm.
do that some number of times. Move on to the next
Hmm.
step of the time. Again, oh, here's
Hmm.
my predicted. Here's my actual. I kind of want them to be a little bit more
Hmm.
update. So it's
Hmm.
optimization based on this loss, but the
Hmm.
loss isn't like, people previously with guidance. What you would do is, I predict my final image. I then
Hmm.
feed that image through a completely separate model
Yeah.
that predicts the pose. I then compare the
Yeah.
pose, and now I have to trace the gradients all the way through this separate network. It's an image that has to go back through the VAE and stable diffusion. Then it has to go back through the
Hmm.
whole of the unit. Then I got my gradients. It's
Yeah.
very, very intensive. And you're saying, oh, actually, I can just kind of hijack it at this feature level, make my predictions
Yeah.
there, and then use that. Does
Yeah.
that make sense?
Yeah, that's exactly correct. And I think one kind of distinction that's really interesting about this is that maybe to summarize what you were saying is essentially, one alternative way of doing this is essentially just getting an estimate of the clean image, which you can get at each time step, and then you can like apply some kind of network on top to estimate the pose on top of that. So there's this paper, for example, called Universal Guidance,
Mm.
which does exactly that. But I think one important thing to keep in mind is that essentially if you were to only feed this, like predicted clean image to your like secondary like pose estimation network, then you kind of, are just doing this in a very disjoint way of like, oh, I have some set of features that generate my image and some like, and I don't use that at all when I'm like predicting the pose. And so one way of thinking about readout guidance is essentially you're bootstrapping on top of the weights or the features of your existing network, which are already very decomposed and very, useful for different tasks. So like it's literally decomposed into like layer 4 of like SDV15 is already very good at semantic correspondence. And I bet it would be like very easy to get a pose prediction out of that. And so you kind of like don't need a lot of extra parameters because you're utilizing these very useful pre-existing parameters that are also used to generate the image. And so that makes it, just like more parameter efficient. And then also, like you said, you don't have to, kind of like do a lot of backprop through other parts of the network, such as the VAE, which you'd have to for like images.
Yeah, fantastic. And it just feels like a very convenient thing in general for guidance. I really liked the idea, and it got played around with for a little while, and then everyone kind of threw it away because it was too computationally intensive. And I feel like
Mm-hmm.
this is something that's a lot of people are missing. Is like, oh, well, if you're doing guidance based on the network that you already have in memory and you're already doing gradients for, it's a lot
Yeah.
cheaper. I mean, it's still slower than normal sampling, but there's so many of these tricks that you
Mm-hmm.
can do, and I really feel like the line of intuition from your whole series of works that you've presented, if that
Mm-hmm.
kind of info was in more people's brains when they were building with diffusion, even things like, oh, I'm editing a local region of the image, or I'm trying to do this specific task. It's like
Mm-hmm.
if you only knew what these networks already know and that it's already like spatially laid out like this, and that you can fiddle with it and interfere with it in these ways. Yeah, I think you could
Yeah.
do it a lot better than the kind of like, oh, we just treat it like a black box and we only work on the inputs and outputs and we hope for the best,
Mm-hmm.
and so then you end up having to do lots of data annotation and lots of workarounds basically to get back to the point that you can kind of shortcut to with this little bit of
Yeah.
intuition. So yeah.
Yeah, exactly. Also, one kind of fun fact is that, when we were doing this shape guided diffusion project, we did like in the back of our heads have like an alternative idea, which we never got to work, which was essentially saying like, oh, we have like these really great pose estimation models, for example, like VIT pose. Can we use guidance in order to like produce images that are like some pose that we want? And so, like you said, I basically just could never get it to work because you have to like go through the VAE. We have these like tiny little like amounts of academic compute, and it was just like so impossible to like get anywhere with it. And so I think it was a really cool journey to kind of like go through this process of like really trying to understand the network and then like coming up with a solution um, that gets back at the same problem statement but like with a deeper understanding of like what's happening inside. So that was really fun. Yeah.
Excellent. All right, were there other things you wanted to say on readout guidance? I know I sort of jumped back to the beginning, but there was some, yeah, was there final thoughts or the
uh,
last section that you wanted to look at?
yeah, I don't know if I have any like particular final thoughts. I think maybe to summarize our whole discussion, I think this idea of kind of understanding the internal features of these generative models is like a very valuable thing to do. Like evidently, these features are very useful for many different things, like predicting image properties and so forth. And so I think this general idea of, bootstrapping on these already like very rich features can be a really great compute efficient and like more straightforward way of like going about a lot of different types of things. Um, I'm trying to think of any other like kind of thoughts along these lines.
I mean,
Um,
maybe one that I can prompt you with is, are there directions you can think of next? So I mean, even the pattern that you've shown here, I can imagine like, oh, I want to first train a readout head that predicts like a face ID hash or something like that, and then I can have personalized generation.
Mm,
Or maybe I want a readout head that's very specific to, some certain types of textures on clothes so that I can do virtual try on, or a readout head for, different types of like satellite image segmentation. So you can start to think of like
yeah.
this copied and pasted for a different type of data. But yeah, then I'm curious
Hmm.
if you have thoughts of like, oh, okay, what's the next thing after that? Like maybe it isn't guidance related, but it's, I don't know, some other
Yeah.
component. I don't know if you have thoughts on directions or even like stuff that you've been working on since
Yeah.
this paper came out.
Yeah, I think I have a lot of various readout heads that I've like tried, but have not like maybe invested too much time into like finishing. So like some maybe more like straightforward types of readouts that other types of control-based methods have like implemented. I was playing around with trying to do like a color palette head where it's essentially like, given a color palette, let me generate like more images with these types of like color themes, and one that's like a bit more non-spatial. So for example, if you look at, I think T2I adapter, for example, has a color palette based generation type of thing, but it's like very
Mm.
spatially biased, and that's more like, oh, for this pixel, I want it to be like purple, like you choose the shade of purple or something like that. So that was kind of one thing I thought was interesting. I think there are a lot of different readout heads that need a little bit more like engineering to get to work. Another one that I found like quite interesting is kind of like this like almost like artifact detection of like, oh, when I generate an image, sometimes there are very like undesirable things in this image that I want to get rid of. So like one common thing is like the hands will like often like maybe you'll have the wrong number of fingers, or like it'll look very distorted. And so I think readout heads that kind of like detect distortions and simply kind of like guide away from them, I
Mm.
think is like another really interesting kind of idea. And I think one last idea that I haven't even like looked into at all, but I think like feels a bit interesting, is kind of this like readout head for domain alignment. Essentially, if I have like a domain that's like super different from like whatever this image generation model is trained on, like for example, if I cared about, like you said, like satellite imagery, or if I cared about, medical images or something like that, if essentially you could have a readout head that could somehow like make you better able to like align to that domain, would be really interesting. I haven't fully sketched out in my head like how this would look, but maybe if it was like medical imagery, then maybe you want to use the features of the space model to predict, some label that's like very important for medical imaging, or maybe even do some very like course level reconstruction of like medical images or something like that. Could
Mm.
be really interesting.
Yeah,
But yeah.
and that's a case where maybe the base features, like the base features that are things like textures and edges and things that it has learned, would still be very useful. But it obviously has the concept of a human because it's trained on millions of humans.
Mhm.
But it definitely
Yeah.
doesn't have a concept of like, oh, the distinction between like diseased liver cells versus healthy liver cells. So you'd have to have like
Yeah.
some sort of more, maybe like fine tune the network part as well at
Yeah,
some point,
definitely.
or at least have some way to bootstrap off. But still, still very like very interesting to imagine what
Yeah.
that might look like.
Yeah, that's a really good point. And I think it's like at the end of the day, the biggest caveat of readout guidance is the upper bound is like of some ability to predict a readout is whether this model ever even understands like some concept or type
Mm.
of knowledge. So maybe there exists no knowledge about anything medical in any way, and you do have to like basically fine tune the base network to get any of that capability. And so that's like one big caveat. Although on the flip side, I think it's interesting in that the readouts give you a bit of a metric or a measure of how much of this knowledge the network encodes. So if your readout doesn't train very well, it kind of like hints that the model may just not know this property.
Mm. Yeah.
Yeah.
Yeah, I'd be so curious to see, you start wondering what this would look like for something like Sora, something trained on video. So there's a time and a physics dimension to it, and much larger
Yeah.
networks trained on lots more data. I kind of wish we had, something even like Stable Diffusion 3 would be really interesting to probe and start fitting some readout
Hmm.
heads on. So Yeah,
Yeah.
I'm curious. Have you tried any of the other, like I know there was the stable cascade models or Deep Floyd, some of these other larger ones that came out more recently than Stable Diffusion 1.5?
No, I haven't tried any other models than Stable Diffusion. Yeah, I mean, I don't have any intuition for like how good. I presume that hopefully it wouldn't be like too bad on like these other networks, but it is like a bit unknown how well they perform on other base models.
Cool. Well, there's a fun project for anyone watching if you want to take the ideas of Readout Guidance and apply them to something else. That's yeah, probably a fruitful place to play.
Yeah.
Excellent. Grace, do you have recommendations? Like if someone, I know you've just released the code. That was one of the things we were waiting for before we did this video. The code for Readout
Hmm.
Guidance is up on GitHub. So is the code for Diffusion Hyperparameters. But yeah, do you have suggestions for like where would someone start if they wanted to begin getting an intuition for this kind of thing? Like would you say, oh, start with the code, or first like try and pull out some features yourself, put in some hooks and visualize things? Yeah, where would you like begin if you wanted if someone said, hey, that video is so cool, I want to do what she's doing?
Hmm.
Yeah, where do they start?
Yeah, that's a good question. I think it depends on the level of like depth that you or like how much coding you want to do for getting this like feature intuition. Maybe let me just start with readout guidance and how one might go about it with like our code base, because I think that is like a pretty nice way to start in that so we do have these kind of like demos where essentially you can just like run through every single cell and it should just run guidance and give you an intuition for what's happening. It takes a bit of a long time to load because I think it has like the images kind of like preloaded or saved in this notebook. But essentially what we do is we have these like Jupyter notebooks where it shows you how to like load a like stable diffusion model, and then maybe you want like some input control. So for this like kind of like spatial control example, and then kind of like running generation according to this control. If you want to poke a little bit more into like the network internals, so all of our like kind of things that we do with network internals are in this like folder called DHF, which basically is like a fork off of diffusion hyperfeatures, but adapted more for this like kind of image generation control use case. So this is where we kind of implement the hooks of like in the stable diffusion folder. All our hooks are mainly on this like in this resnap.py file, where essentially we just like have like a feature saving like hook when you like for your unit, such that it'll like save the features for you and like give it back out.
Mm-hmm.
And so that's kind of like where we implement that. And in general, I think like the coolest thing to look at is like kind of the features. So like you can do PCAs on top of the features and see cool things. You can look at how like these like readouts evolve over like the diffusion process. Yeah, let me think of other things. I think also one big tip when like you're doing this kind of like investigation is kind of looking at predicted x zeros across the like diffusion process.
Mm.
So yeah, it's kind of unfortunate that we don't. I guess this is an example of like predicted x zeros. Oh no, this one doesn't have any predicted x zeros. It's kind of sad.
Yeah.
Let's see. I should implement that as like a new feature in our code base. I don't know why. Like, I never added that as like an additional output because it's pretty simple. But we have like in this figure, let's see. Yeah, so these are examples of predicted x zeros in this like second row, which is essentially like, oh, okay, across the diffusion process, if you were to look at like the latents directly, then it would like look really noisy and uninterpretable. But in general, it's way more useful to look at predicted x zeros because it gives you a better intuition of like what exactly is like happening in the network in a more like perceptually like salient way that makes more sense, even though the amount of information is actually very similar between this
Yeah.
like noisy version and this like predicted x zero. So I think that's always very helpful when you're doing any kind of like analysis. And you can get it with most samplers. This is like a very core like feature of the DDIM sampler. And I think a lot of more recent samplers after that also have that as a feature, but it
Yeah.
also
The,
depends on which sampler you use.
all the Hugging Face ones didn't have it, and it really bugged me. So any of the ones that do, it's because I got fed up and put pred x0 as one of the returns. Because I
Mhm.
don't know why people don't look at that. Yeah. So that's some really good advice. I think there's also like if anyone's done, for example, the diffusion models course from Hugging Face or anything that covers guidance,
Mm.
you'll know it's an optimization loop. And so if you go look through the Readout Guidance code, I can't remember what file it in, but somewhere you'll find like
Mhm.
optimizer.step. Like if you search for that,
Yeah.
you'll find the place that's actually like, oh, what is the gradient? Like, how do I update my latents to reduce this loss that I've calculated? And then, okay,
Yeah.
and visualizing the normal of that gradient or something is also like, oh, which parts of the image are set to change lots.
Mm.
Yeah, so
Hmm.
that would be another good place, I think, for people to poke, start to get a feel for
Yeah.
what's going on.
Yeah.
Yeah.
Yeah. It's a really good point.
Um, Excellent. Okay, I really hope we inspire someone to go fiddle around with these things because, yeah, it just seems like such a cool space.
Yeah. Yeah. Definitely.
Awesome. Okay. Well, I think we'll end the video there. I'm hoping like at some point I want to have time to play with this and do a follow up where we like
Hmm.
use and abuse this for some other fun purposes. But this I think has been so instructive. I really appreciate you coming on, and yeah, I think this will inspire some people to go mess around with these cool models.
Yeah. Thank you so much for having me. And yeah, hopefully everyone learned a lot and enjoyed the video.